In this Q&A video, we're going to answer the question, how do I protect tails over 3 meters long while maintaining selectivity? Just before we explain the answer to this question, please be aware that this video is one of a series that we've made on the subject of circuit protection. They can be viewed individually, or you can click the link in the description below to view them as part of a free online training package to help you with your CPD, and you'll receive a certificate to prove you've completed the course. The answer to this question comes down to a combination of regs in BS 7671 that actually relate to the emission of overcurrent and fault protection devices, but also includes a sprinkling of direction from local distribution network operators. Bear in mind also that certain DNOs around the country state a maximum length of 2 meters for meter tails, so watch out for that. The regs in BS 7671 that relate to this subject are centred around the emission of devices that provide overload and fault protection. We find in regulation 434.3 indent 4 that we can omit a protective device for fault protection at 4, the origin of an installation where the distributor installs one or more devices providing protection against fault current and agrees that such a device affords protection to the part of the installation between the origin and the main distribution point of the installation where further protection against fault current is provided that both of the following conditions are simultaneously fulfilled. The wiring is carried out in such a way as to reduce the risk of fault to a minimum, see item 2 of regulation 434.2.1, and B, the wiring is installed in such a manner as to reduce to a minimum the risk of fire or danger to persons. So it's up to the distributor to agree that the fuse in the service head provides sufficient protection to the meter tails. But where do they get that 3 meter value from? Well, the regulation referred to there is in this same section of the regs, but relates to installing protective devices in positions other than where the conductor size changes. And in that regulation, 434.2.1, we find direction that in those circumstances, the conductor shall not exceed 3 meters in length. So the idea is that the longer a cable gets, the higher the likelihood of it receiving or causing damage. So by putting this limit of 3 meters in place, it reduces the chances of this happening. Now, while this figure doesn't appear directly in the regs concerning the emission of devices, it's significant that it appears in regulations of a similar nature and clearly shows that the authors of BS 7671 consider a maximum length of 3 meters to contribute to minimising the risk of a fault. And in fact, one of the DNOs specifically refers to this regulation in their guidance on meter tail length. So what can we do when a consumer unit is more than 3 meters from the supplier's cutout in meter? Well, in that case, we do need to provide overcurrent and fault protection, so we can pop in a switch fuse like this one and then change the fuse out in it for a smaller one. Certainly we can, however, this then raises the often misunderstood issue of selectivity. Selectivity, which we used to refer to as discrimination, is the principle that if you've got a cable protected by a protective device that feeds other circuits with protective devices protecting them, then a fault on one of these sub-circuits should not cause the protective device feeding the sub-circuits to disconnect. This is for reasons of safety and convenience. The classic example is in a hospital. You wouldn't want a faulty kettle to trip off the circuit supplying a life support machine, or perhaps some kind of safety circuit in an industrial building. So what should the value of this smaller protective device be to ensure we get the right device tripping when a fault occurs? Can you just stick the next size fuse down in and it will all be okay? Well, the regulations give you a few options to figure it out for various scenarios, but let's just stick to overcurrent protection for now. Regulation 536.4.1.2.1 under the heading General Requirements states, where selectivity is required, as shown in figure 536.1, the design shall be verified either by desk study, taking into account the relevant product standards and the manufacturer's literature, or appropriate software tools where information is provided by the manufacturer for this specific use, or tests in accordance with the applicable product standard in order to achieve the correct test performances and reproducibility, or manufacturer's declaration. So basically you get the data for the devices in question and compare the areas of the curves to make sure they don't cross over. And this can be done manually or with some piece of software like Amtech. However, this can be a bit tricky, and BS 7671 gives you a rule of thumb to go by in Annex 53, namely A53.4, where it states, selectivity in case of overload is verified by the comparison of time current characteristics of the fuses involved. The total operating time of the fuse on the load side must be lower than the pre-arcing time of the fuse on the supply side. Fuses to BSEN 60269-2 of the same utilisation category, with rated current of 16 amps and above, will provide total selectivity if the ratio of the rated currents is 1.6 to 1 or greater. Separation of the characteristics in both the time and current axes provides selective operation in this zone. The bit that we're really interested in is in the middle there. It's the part that talks about the ratio of rated currents being 1.6 to 1. That means that if the upstream fuse is 1.6 times the downstream one, you should achieve selectivity. So if you have a 100 amp main fuse like this one here, and you divide 100 by 1.6, you'll get an acceptable fuse size. Doing that calculation gives us 62.5. So if we install a 60 amp fuse in here, then that's all good. However, this is where things can get a bit challenging. Going back even just a decade or so, a 60 amp supply was usually more than enough for a typical home with gas heating and cooking appliances. With all the increases in electrical equipment that we're using at the moment, such as EV charge points, heat pumps and electric cooking equipment, you could run up a current demand above this value quite easily at certain times. One way to mitigate the risk of blowing this 60 amp fuse is to install some load curtailment into the EV charge point, or maybe limit how much current it can draw. But let's say that we need that extra current. What can we do? Well, this is where a bit of practical engineering needs to come into play, and you have to ask yourself, do we actually need to achieve full selectivity in this case? Think about it. One of the fundamental points of achieving selectivity is that you don't lose healthy circuits when you don't need to. We're not installing a fuse here to protect a submain due to a change in cable size, etc. We're doing it because the DNO won't allow us to protect our tails if they go over 3 meters long, or in some cases 2 meters. So if a fault occurs on our submain causing this fuse to blow, and this one, the DNO's one, beats it to the punch, we've not really caused any greater harm or disconnected anything that we wouldn't have lost if this fuse had blown instead. You could argue that it's less convenient to replace the DNO's fuse than the accessible one in here, but that argument doesn't really hold water when you think about the hundreds of thousands of properties where if a fault occurs on the tails, we blow the DNO's fuse because it's all that's protecting them. So as long as you size the submain correctly and feel comfortable justifying the fact that you're only achieving partial selectivity at the origin of the installation, then you may be able to install a bigger than 60 amp fuse in here and use the extra capacity if it's available. And that concludes this series of videos. If you found it helpful, why not click the link in the description below to complete our free training package on this subject to help you with your CPD and receive a certificate as well. All that remains in this video is to say thank you very much for watching.